What's going on, guys? Welcome to the second video in the series tackling ordinary differential equations. Now we will talk about linear ordinary differential equations. Now, ordinary differential equations are of the form dy over dx plus p of x times y equals q of x. Now, you may say, well, can we just separate P and Q of X and then Y? Most of the time, for equations of the form like this aren't necessarily separable, so we have to tackle this in a different way. Now, how do we get around solving this? Well, remember the product rule. It states that uv and then you have like the derivative with respect to x. This is u prime v plus u v prime, right? What if we had like f of x times y? What if we had that? Well, we would have f prime of x times y plus uh dy or plus then f of x and then the derivative of y, which is dy over dx. We almost have this form here. If f(x) is just 1 and then f prime of x is p of x, it would be fine. But that wouldn't be interesting. It would be boring. So what do we need? What do we need in order to for this to match this? What do we need? Well, we can multiply both sides here by what we call a special integrating factor, mu. So this would be the resulting thing. Now, we just multiplied both sides by mu of x. What does this mean? Well, it takes the place of f of x in here. Look, mu of x times dy over dx. But there is this right here. P of x times mu of x, which takes the place of f prime of x. So this and that match, this and that, they match, but this and that have to match as well in order to make this possible to solve. So what is mu of x? Well, we know that f of x dy over dx is equal to mu of x dy over dx. We can divide both sides by this one, so f of x is mu, just mu of x. Now, f prime of x y multiplied by no, just that, equals p of x mu of x and then y. We can divide both sides by y. We're left with f prime of x equals p of x mu of x. Now, we just established that f and mu are essentially the same, so we can differentiate both sides and we get the same thing. Right. And then we can change this into mu prime of x. So that becomes that. Then p of x mu of x. Now let's try isolating p of x here. So we get p of x equals mu prime of x over mu of x. Here's the crazy part. Let's just there we go. Let's integrate both sides with respect to x. Now what happens? This remains as the integral of p of x. P of x can be any function, so we don't know the integral of that. But this is especially interesting because it is the form ln of mu of x, right? Uh, for plus c, we just say c equals 0. It doesn't really matter in this one. But we have ln of mu of x and the integral of p of x dx here. To isolate mu of x, we have to raise both sides. We have to raise e to both sides, sorry. So now mu of x equals e to the power of the integral of p of x dx. We will be using this in order to solve a linear differential equation. So let's solve our first example. Dy over dx plus 3x squared y equals 6x to the power 5. First thing you do is to check if this is in accordance to uh, the linear form. So dy over dx here, check. A function of x with y, check. And then a function of x here. There's no stray y's. Anyway, check, check, check. So it's a linear ODE. Now we can use the special integrating factor mu here, which we know is e to the, what is p? This is p of x. So 3x squared dx. We know the integral of 3x squared is just, oops, sorry, x cubed plus c. Let's just ignore c for now. It doesn't even matter in the solution anyway. So let's proceed to the next step. Multiply both sides by this thing. So e to the x cubed dy over dx plus 3x squared e to the x cubed y equals 6x to the 5 e to the x to the cube. This is guaranteed to be a product rule of this form, right? Because the formula says that it is going to be this form, the product rule. And then the next part is to, well, just copy this one. Now, we have to integrate both sides with respect to x. Now, the fundamental theorem of calculus states that the integral of a derivative or the derivative of an integral, whatever you want, is basically canceling each other out. So this just becomes e to the x cubed y. This is what we need to solve. The integral of 6x to the 5 e to the x cubed dx. So let's put it here. So what can we do here? Well, let's try separating x cubed such as so. So x cubed e to the x cubed here. And then we multiply it by 6x squareds because 6x squared times x cubed is 6x to the 5. So that's perfect. Let x cubed equal to u. Now, 3x squared dx equals du. Now, 6x squared is twice 3x squared, so we can put 2 and then du here, since 6x squared dx equals 2du, right? Now, x cubed becomes u, x cubed becomes u, and we're left with our integral, ue to the u du. This is a classic case of integration by parts, and we can use the DI method for any, and I mean any integration by parts uh, problem. So plus, minus, plus, and then we can add as we go. So we put u in here and e to the u here. There's a there's the LIATE or the LIATE for acronym for what you put in the D columns. Logarithms, then I forgot what I was stands for, but it's something. Then A is algebraic. Then T is anyway. I forgot what it was for. Anyway, I don't recommend memorizing LIATE. I recommend just having an instinct for it. Practice over and over until you get what is appropriate in the D column and appropriate in the I column. For this one, U is appropriate in the D column because it goes to 0 and we can stop there. Then e to the U here, e to the U here. So the answer here is 2, because 2 is in here. So 2u e to the U minus 2 e to the U. That is the answer here. Or if we convert back to x, we get, let's copy e to the x cubed here. E to the x cubed y equals 2x cubed e to the x cubed minus 2e to the x cubed. Now, we forgot plus. See? Here. So now we can divide both sides by this, e to the x cubed. It's easy to divide it, by the way. So y equals This and that cancels, so 2x cubed. This and that cancel, so it's 2. So that's that easy. But we have to put c over e to the x cubed right here. So yeah, this is the general solution. And there we go. We're finished with this one. Next. All right. dy over dx plus y times tangent x equals cosine x. Now, this a linear? So there's dy by dx, there's y, there's a function of x, and then there's cosine x. I think this is a slam dunk. This is indeed uh, a linear ODE. So now we just have to find the special integrating factor. E to the power, e to the integral of tangent of x. Now, if you remember, the integral of tangent of x is ln of secant x. This does mean that we can cancel e to the x and secant x, and then we get secant x. Now, the absolute value, you don't need to worry about that. Again, this is just a special integrating factor. We don't need a c or whatnot. It's too much stress, you know. So this is going to be it. So now, multiply the special integrating factor on both sides. So we get secant x dy over dx plus y times secant x tangent x equals cosine x times secant x is 1. All right. Because secant is 1 over cosine. So now this is obviously d over dx times secant x and then y. Let's put y here so we don't confuse it with secant xy. Then we put 1 here, just 1. So now we integrate both sides with respect to x. Again, derivative and an integral, they cancel each other out, so we just get y secant x. And then on the other side, we got x plus c. So y then is equals to, if we multiply both sides by 1 over secant, 1 over secant x, as we all know, is just cosine x. So we just multiply both sides by cosine. So x cosine x plus c times cosine x. Okay. Now we are given the initial value as y of 0 equals 0. So this is going to be a specific equation. So 0, 0, that's easy to remember. It's just the origin. So we put 0 in everything. 0 times cosine of 0 plus c times cosine of 0. Now, cosine of 0 is just 1. So c, so just remains 0 times whatever is just 0. And then 0 is 0. So 0, c equals 0. So this one doesn't exist because it's just 0. So y equals x cosine x. That is the specific solution for this one. And that's all for now. I'll see you in the next part.